Okay, so now that we have three equations for our energy and we've quantified them, let's go ahead and take a look at some simpler problems, and then we'll take a look at more complex AP problems in class tomorrow. So first thing we want to do is go ahead and define our system. So remember, our system is any object that can store energy and any field that can store energy. So here we have the car as an object that can store energy, so it can store kinetic energy in its motion. We have the spring, which can store elastic energy, and then we have the gravity field produced by the Earth, which can store gravitational potential energy. So let's see, in the initial state, it is moving. So let's go ahead and just give it 2 bars of kinetic energy. I've got to define a point of zero potential, so using my general rule of thumb, I'm going to use the floor. So this blue line will represent where my potential energy is 0, or that y is 0. So that means I have no gravitational energy initially, and there's no spring energy initially. In the final state, its velocity has gone to 0, so no kinetic energy. It is still not a height above the ground, but the spring is being compressed, and since energy must be conserved, I'm going to put 2 bars there. So I have my initial kinetic energy must equal my final elastic energy. And that just comes again from our conservation of energy, which is initial energy must be equal to final. So initial kinetic energy is 1/2 mv initial squared equals the elastic energy in the spring, so that's 1/2 k delta x squared. So let's see, we got 1/2 on both sides, so I'm going to go ahead and get rid of that. And I'm being asked for by how much the spring is compressed. That's asking for delta x. So let's see, we got mv initial squared equals k delta x squared. So I'm going to go ahead and divide both sides by k, and then take the square root. So I get that delta x is equal to the square root of mv I squared over k, which is going to be the square root of the mass, 8 kilos, the initial velocity, 5 meters per second, and that's squared, over k, the spring constant, which is 50 newtons. So I plug that in, and I get an answer in meters, because we are talking about a horizontal displacement of the spring here. And let's take a look at number 2. So number 2 has something interesting introduced to it. So now we're taking something we talked about last time, a frictional force, and introducing it into energy. And this poses a unique situation. So first 2 things, define my system, and then define my point of zero potential. So objects that can store energy are the car. Fields that can store energy are the Earth. And let's see, point of zero potential, I'm going to make it at the bottom of the hill. So y equals 0 at this point, and that means my gravitational potential energy at that point would be 0. So looking at the top of the hill, there is no velocity. There is potential energy, because it says it is 5 meters above the ground. So I'm going to go ahead and give it 3 bars. And there's no elastic energy. At the bottom of the hill, there is kinetic energy. There is no gravitational energy, and there is no elastic energy. So here, though, they say that 10% of the energy is dissipated by friction. So that means from the top to the bottom, I lost 10% of the energy that I started with. So where is that energy going, though? So normally I would draw 3 bars here. I'm going to draw a little less because I lost some of that. And where that energy is going is into what is known as internal energy. So let's take a moment and talk about internal energy, sometimes abbreviated as the internal. So what is it? It's energy stored at the microscopic level. So the energies we're dealing with mainly, kinetic, elastic, and gravitational, are all energies at a larger scale, or macroscopic energy. Energy stored at the microscopic level is something that you guys would have seen in AP Chem or Honors Chem in the previous year. And what it is actually thermal energy, which is just the kinetic energy of the particles. So typically, energy that is reduced due to friction ends up as thermal energy. If you take your hands and you rub them together, you generate heat between your hands. And what that energy is the particles moving faster in your hands. So in this case, as the car goes down the ramp, so there is friction between the tires and the ramp and the hill. So if we have the tire beforehand, at the microscopic level, the tire is made up of all these internal particles. And the particles are vibrating back and forth a little. Now, as it goes down the hill, friction causes it to heat up. And so what happens to that tire is those particles actually gain energy and they start moving a little quicker. So the particles in the tire now have more internal energy. The molecules have taken some of the gravitational energy that was then transferred into them by friction, heating them up and increasing the internal kinetic energy of the particles. So that's where that energy goes. So friction here took 10% of the energy as it's going down the hill and just transferred it internally to the system in terms of particle motion. Now, we won't really deal with anything very in-depth in particle motion, as that's up to AP Chem. However, in cases like this, you should be able to do a problem where you have to figure out, well, what this is telling me is that my final energy that I end up with is only 90% of what I started with. So 0.9 of my initial energy. And according to my energy bar chart, my initial energy was gravitational, mg delta y. My final energy is kinetic, that's been reduced, and it is 1/2 mv squared. So here, I want to find the final velocity, so I just got to get v squared. I'm going to multiply both sides by 2. So 2 times 0.9 is 1.8. So we have 1.8 mg delta y equals mv squared. Now we got mass on both sides, that cancels, and next all I have to do is take the square root, and we end up with v equals the square root of 1.8. G, we're going to use 10, and then delta y here is 5 meters. So that's how we would deal with things like internal energy and friction. Now, number 3. So we have a block placed on a spring, compressing at 0.3 meters. What height does a block reach when it is launched by the spring? So no friction here. that's clearly stated, so I'm not going to worry about having to deal with anything stored as internal energy or any changes in internal energy. So I need to set a point of zero potential. So they've labeled height as 0 here, so I'm just going to go ahead and call that y equals 0 and EG equals 0. So I know in its initial state then, it has no gravitational potential energy. The spring is compressed 0.3 meters, so it is going to have some elastic energy. I'm going to give that 3 bars, because why not? It is not moving, so it has no kinetic energy. I should have defined my system, so all the things that can store energy, all the objects are the block, and then the spring. All the fields that can store energy in this case are the field created by the Earth. And then, let's see, in its final state, its velocity is 0, so no kinetic energy. It's no longer compressing that spring, so no elastic energy. And let's see, gravitational energy, it is a height above the ground, so that means all my energy had to be transferred into gravitational. So by conservation of energy, I know this statement must be true. Now, let's see, my initial energy was elastic, so that's 1/2 k delta x squared equals, or I guess I want to be a little more explicit here, so that would be my elastic energy initial must be my gravitational energy final. So 1/2 k delta x squared equals mg delta y final. Here I'm asked for what height, so I want to get delta y by itself. So I'm just going to divide both sides by mg, and I'll get 1/2 k delta x squared over mg. This tells me that delta y is equal to, let's see, k is 100, so 1/2 times 100, 50, delta x 0.3 squared over the mass, 500 grams, or 0.5 kilograms, times the gravitational field constant 10. So I plug that in, and we get an answer in meters, because we're talking about delta y, a vertical displacement here. All right, and now number 4. So we have a bullet that strikes a block of wood, which exerts on average a force of 50,000 newtons opposing the motion of the bullet. How far does the bullet penetrate? Okay, well, let's go ahead and set a point of 0 potential. So I don't want to really have to deal with changing heights. So I'm just going to go ahead and set my potential line actually to be at the center of the bullet. So I'm saying this height is y equals 0, where my potential energy is 0. So that way, I don't have to worry about trying to figure out how high the bullet is off the floor. I'll just call this point 0 potential. So let's see. Initially, it is moving, so it's got some kinetic energy. I'm going to give it 3 bars. I've set my potential to be right in line with the bullet, so it is not above or below my line of 0 potential, so it is storing no gravitational energy, and it is not compressing a spring. Once again, I should define my system first. So all the objects that can store energy would be the block and the bullet. All the fields that can store energy would be the gravitational field from the Earth. Now, in the final state, it's not moving, so no kinetic energy. It is not a height above my potential. The center of mass of both the bullet and the block are along my line of 0 potential, and there is no spring being compressed. So now the question is, well, where did the energy go? Well, it had to be stored internally. So to double check that statement, I want to make sure that there's a frictional force. Well, as soon as the bullet hits the block, it experiences a force of 50,000 newtons opposing its motion. So that's our frictional force. So what's happening in terms of internal energy, for the bullet in the block, at the moment of impact, or right before the impact, we have a block with particles, and we have a bullet with particles. So the block has kinetic energy itself. The bullet has kinetic energy, the block doesn't. And then later, as it's brought to a stop, the bullet ends up inside the block. And it's created some sort of hole into it. And what happens is the friction of the metal of the bullet against the wood creates heat, increasing the thermal energy of the particles inside both the bullet and the block. So now all this kinetic energy that the bullet had is now stored internally in terms, or at the level of the particle microscopically in terms of the particle's vibrational motion. So all my energy is stored internally. So now how far does the bullet penetrate? Well, I can't really use energy here because we don't really have a set equation for internal energy. Maybe we can try some kinematics, because I'm thinking if we have the bullet, we have the block. This is at the moment before impact. So right here, let's call this x equals 0. The bullet is going to travel some distance into the block. And we want to figure that out. So what we're trying to find is this delta x. Well, I know that initially it's moving at 350 meters per second. Here, its final velocity inside the block once it comes to a stop is 0 meters per second. Now, let's see, I have a final velocity, I have an initial velocity, and I want to find displacement. So for any kinematics equation, I need 3 variables that would allow me to find the fourth. So that means I either need time or acceleration. Well, I don't know if I have anything that can really help me find time, but I do have force. And from last section, we actually know that force and acceleration are linked together. We know that the sum of the forces acting on an object equals the net force. In this case, because we're talking about a delta x or displacement in the x direction, then I just want to sum the forces in the x direction here. And the bullet is decelerating. It's going from 350 to 0. I know that my net force can either be 0 or ma. Since this is unbalanced, but given by the fact it's decelerating, that means I need to use ma. So the only force acting on the block in the x direction is the force of friction. There's nothing actually actively pushing it to the right. It's only the force of friction acting to the left, right? If we were to draw a force diagram for the bullet, once it hits the block, it has the frictional force acting on it, which is the block pushing back on it. It's got a force of gravity downward, and it's got a couple normal forces acting on it as well. But the only thing we're concerned about is this force here. Force of gravity doesn't really matter because we're talking about the x direction. So, because the force of friction is going to the left, I'm going to make that 50,000 negative equal to its mass, 25 grams. So I want to convert that into kilograms, or 0.025 A. So A is equal to negative 50,000. over 0.025. Now my acceleration is going to come out negative, and I just want to make sure this makes sense. If we remember all the way back to kinematics, if something is slowing down, its acceleration and velocity vectors must be opposite. This thing is moving to the right and slowing down, so its velocity vector must carry an opposite sign, being negative. So it makes sense that my velocity is negative here. Now I can actually use a kinematics equation to figure out delta x. I could use this equation here. I know that my final velocity is 0. Then if I subtract v0 to the other side, negative v0 squared goes to a delta x. So then I get delta x is negative v0 squared over 2a, or that delta x is negative, v0 squared, so 350 squared over 2, big old number. And in this case, let's see, so 350, 50, we get 0.03 meters or 3 centimeters. So the bullet goes 3 centimeters into the block before coming to a stop. The initial kinetic energy it has is turned into internal energy stored via the heat or increase in temperature or thermal energy of the particles.